Okay, we are going to discuss maximum likelihood estimates in this video. And I just want to point out that there is a link to this Colab notebook. And so if you are a student of mine, we have begun discussing this in class. So we're going to kind of pick up with what we've discussed so far. And if you're not familiar with this, you may want to scroll back through this Colab notebook and familiarize yourself before jumping into this example. But the general goal of estimation is to find or estimate the unknown value of a population parameter that we typically denote with the Greek letter theta. So this is a fixed value, but we don't know what that value is. It is summarizing the entire population. So if we want to estimate that value, what we can do in statistics is we can pick a random sample from that population and then look at characteristics from our sample and use that to formulate an estimate that we call theta hat for the value of the population parameter. And there are different methods that you can do to come up with estimates for the population parameter. In this video, we're going to talk about how we find maximum likelihood estimates. And so for a maximum likelihood estimate, recall one way that you can think about that kind of informally is we are going to find what is the most likely value for the population parameter theta, given we have observed a random sample of values that we denote x1 up to xn. So key to this process is first finding the likelihood function, which is the probability of observing the sample that you have. So you can find this likelihood function taking the product of either the probability density function or the probability mass function evaluated at each of the values in the observed sample. So you can think about this likelihood function as giving the probability of observing your sample, and that is going to depend on what the value of theta is, and that value theta is unknown to us. So we're going to kind of pick a sample, and then from that sample, we're going to estimate theta with its most likely value. And that's what we call the maximum likelihood estimate. So if you want some sort of motivating example to help guide you with this process, imagine that you are given a bag with a bunch of different colored balls that are all the same size, and you're asked to guess what proportion of the balls in the bag are green. And you're allowed to pick a ball 3 times from the bag. So you go up and you do an experiment. You pick a ball from the bag, you look at what color it is, and then you realize that you want to replace it. And then you pick again, and you do this 3 times with replacement, and you have 1 out of the 3 balls that you picked were green. And then you're asked to, based on that sample, what is your estimate for P, the proportion of all balls in the bag that are green? So that's essentially what we're trying to do here. For our example, let's consider that you did this experiment and 3 other friends of yours did the same exact thing. So they all went up to the bag and they picked 3 times with replacement and counted how many green balls they picked out of 3 attempts. So underlying this process is binomial distribution. Each person repeated this process 3 times and with replacement, so the probability of picking a green ball each time is P. And P is unknown to us. And we can think about you and your 3 friends each as collecting 1 data point from the population. So your observation of 1 out of 3 is the first value in our sample. Somebody else had 3 out of 3. Someone had 3 out of 3, and then the 4th person had 2 out of 3 that were green. So based on this information, let's find the maximum likelihood estimate for the population proportion P. So the first step would be to find the likelihood function, and this likelihood function is going to be a function of the population proportion P. which we don't know. But we do know our population is binomial. Each of these values in our sample is coming from a binomial distribution where the number of trials is 3 for each person. So we could go ahead and plug 3 in for n, and then we can plug in the different values for x that were observed by the 4 different people in our sample. So we can plug 3 in for n in this formula again, and then I'm going to plug in 1 for x. And this first term is giving me what would be the probability of getting 1 out of 3 balls that are green based on this proportion p, which is unknown to us. This second term is the probability that person 2 got 3 out of 3, and so on. And then because each person gathering their sample is independent of the other person, each of these experiments is independent. So the probability that all 4 of these things occur, we can compute just by multiplying their probabilities. So that's what the likelihood function is telling us. What would be the probability of observing the sample that we just found given or based on the population proportion P. And what the maximum likelihood estimate is going to do for us is it's going to estimate P with the value that maximizes this likelihood function. So before we go on into the maximize step, let's simplify this a little bit. So we can multiply the coefficients that we get from this combinatorial operation as 3 times 1 times 1 times 3. And that's where this 9 comes from. We can group the p's together. P to the first times p cubed times p cubed times p squared gives us p to the 9th. And then the 1 minus p terms, we have 3 of them. So here we've simplified the likelihood function. And again, what you can think about this is I plug in a value of P, and the output is the probability that we would have observed our sample with that value of P. And so the next step in this process is to go ahead and find the value of P that maximizes the likelihood function. So this is going to tell us what is the most likely value for the population proportion P. So we go ahead and take this likelihood function that we just found. We take its derivative. And so to take its derivative, we can apply the product rule to this. So I can think of the first function as 9p to the 9th. So I take the derivative of that, which gives me 81p to the 8th power times 1 minus p cubed. And then the product rule says we then take the product of the first function times the derivative of the second function. So we're applying the product rule and the chain rule to this expression, and that gives us the derivative down here. And then I would like to figure out when is this derivative equal to 0. I want to find the critical points, since the maximum value of L is going to occur either at an endpoint of our domain or a critical point. So to find when this expression is equal to 0, we can factor it. So I'm going to factor a 27 out from both of these constants. That's where this leading 27 comes. I'm going to factor a p to the 8th power out from both terms and a 1 minus p squared from both terms. So that is the kind of common factor that I pull out. And what's left over from the first term is 3 times 1 minus p. And from the second term, we have one factor of p left over. And then we can simplify this factor to minus 4p plus 3. So the derivative factors is a polynomial. We've got 3 factors. So this derivative is going to equal 0 when p is equal to 0, when p is equal to 1, or when p is equal to 3/4 or 0.75. So those are the critical points for our likelihood function. If you want to think about a domain for P, I suppose it is a proportion. So P has a minimum value of 0 and a maximum value of 1. So the endpoints of our domain of interest for P also happen to be critical points. So the maximum is going to occur at one of these three values for P. And we want to check the value of the likelihood function at each of these values. So if we go back to the likelihood function, when P is equal to 0, the likelihood function is 0. If there were no green balls in the bag, the proportion was 0, then it would be really impossible to have observed the samples that we got. We wouldn't have had any samples that had any green balls. If P were equal to 1, the likelihood function also gives us 0. This makes practical sense since if all of the balls were green in the bag, then everybody would have picked 3 out of 3 green balls. So there's no chance that P is equal to 1. So that kind of leaves the last critical value, the last critical point at 0.75. And down here, I just entered in a code cell what is the value of the likelihood function when P is equal to 0.75. And that comes out to about 0.0106. The value of P that maximized our likelihood function was 0.75. So we're going to denote this estimate. We're estimating a population proportion. So we denote it with P. We put a hat over it because it's an estimate. And we put a subscript of MLE to denote that it was an estimate obtained using the maximum likelihood estimation process. So our maximum likelihood estimate is 0.75. And it's always nice to make sure that these estimates make intuitive sense. That's a good property for an estimator to have. And this makes sense in this case since you can think about pooling the 4 samples of 3 balls that we picked. It's no different than considering that as one sample of 12 balls that were picked, since each time we picked with replacement. So if we grouped all of our observed green values together, which was 1 plus 3 plus 3 plus 2. So that's where this 8 came from. So altogether, out of the 12 balls that we picked, 8 of them were green. So that would make sense that an estimate of 8 out of 12 or 0.75 makes sense. So this is the proportion of all of the balls that were picked that were green. And that's exactly what the maximum likelihood estimate was. So these estimates, MLE estimates, are usually intuitively, they make sense in the end. So just to summarize, overall, the steps for finding the maximum likelihood estimate are first, we find the likelihood function, then we want to maximize the likelihood function. And so we can do that by finding the critical points of the likelihood function, taking the derivative, setting the derivative equal to 0, and then comparing the value of the likelihood function at each critical point, and the value that gives us the largest value of the likelihood function, that's going to be our MLE estimate. Okay, thanks everyone.